In today's video, we're going to prove the inverse function theorem in 1D. If you watched yesterday's video, this is really the same argument as we did yesterday. So the meta lesson for today is that studying a particular example can go a long way when it comes to understanding big results. In my opinion, this is a useful study tip. If you encounter a proof of a big theorem that is too terse to understand, you might want to try to work it out in a specific example that you're already familiar with. All right, let's start with the statement first. Let f be a real value function of a real variable defined on a closed interval ab. If f is injective and differentiable with f prime of x not equal to 0 for all x in ab, then f inverse is differentiable with f inverse prime of y equals to 1 over f prime evaluated at f inverse of y. This is a very useful result. For example, you can use it to derive the derivative formulas for inverse trig functions, so to say. And also beyond that, many special functions in applied mathematics are defined using the inverse function approach. For example, elliptic functions can be defined as the inverse of elliptic integrals. But we're not going to get into those advanced applications today. Our focus today is to prove this theorem. Before we present the correct proof, let's first address a very common mistake. So this is a wrong proof. First, let's write x equals to f inverse of y. Then by the definition of inverse functions, we have f of x equals to y. This is of course valid. Then we're going to implicitly differentiate with respect to y on both sides. Remember now, x is treated as a function of y. So on the left-hand side, really we have a composite function. So differentiating with respect to y, we might consider using the chain rule. So the left-hand side now reads f prime of x times dx over dy. And the right-hand side is just the derivative of y itself, which is 1. And then we can rearrange this and get dx over dy is 1 over f prime of x. And since x is f inverse of y, we can write the equation above as d over dy acting on f inverse of y is equal to 1 over f prime f inverse of y. So it seems like we have obtained the result that we wanted, but this is a wrong proof. Let's look at why. The proof is wrong because in the implicit differentiation step, that is f prime of x times dx over dy equals 1, we have used the chain rule. And the chain rule rests on the assumption that the function x of y, aka the inverse function, is differentiable. But this is something that we wanted to prove, so there is circular reasoning going on here. So let's recall the chain rule. It says if a function f is differentiable at x equals a, and g is differentiable at x equals fa, then the composite function, and to be honest, I have no idea to this day how to read g circle f. I just read g circle f. Might be wrong, I'm sorry. This composite function is differentiable at x equals a, and the derivative at x equals a is g prime of fa times f prime of a. Now we can look at the correct proof, and before that we need one more fact. So here is a crucial fact that we need in a proof of the inverse function theorem. It says if a function f that maps the closed interval a to b into R is continuous on the interval a to b and injective, then its inverse function f inverse is also continuous. This is in fact a highly non-trivial fact. Proving it is well worth making its own video. And just to help us appreciate the non-triviality of this fact, we remark that in general, it is not true that continuous injective functions always have continuous inverses. So here's a counterexample. Consider the function f that maps the interval 0 to 2 pi, which is closed on the left endpoint and open on the right endpoint, into the unit circle S1 on the plane. And any number t in the interval 0 to 2 pi gets mapped to a point cosine of t sine of t. In fact, we can describe this function geometrically. So imagine you have a piece of string that has length 2 pi, which is of course equal to the circumference of the unit circle. So now you're going to select a random point on that string and cut it there. And next, you're going to place one end of that string at the rightmost point on the unit circle, that is the point 1, 0, so that it follows the circular arc. We do this in a counterclockwise manner, and the endpoint of that string would have coordinate cosine of t, sine of t, and that's the value of the function f of t. This is a verbal or geometrical description of the function f. It's clear to see that this function is continuous because the components cosine of t and sine of t are both continuous. And also f is injective. So if you cut your string initially at a different location, the point we end up getting on the circle would also end up being different. So that means f is injective and f inverse must also exist. And the geometric meaning of f inverse is also clear. So for an arbitrary point on the unit circle, the f inverse evaluated at that point is the length of the circular arc connecting the point 0, 1 to our chosen point, and the arc always extends in a counterclockwise manner. The punchline of this counterexample is that the f inverse is not continuous, despite the fact that f is. So the problem arises at the point 1, 0. Imagine a point P on the unit circle approaches the point 1, 0 from above, then the f inverse of P would approach 0. And on the other hand, if the point P approaches 1, 0 from below, then f inverse of P would approach 2 pi. To summarize, approaching the point 1, 0 from two different directions give two different limiting values of f inverse. F inverse does not have a limit at 1, 0, and therefore f inverse is discontinuous at 1, 0. So now we should be able to appreciate this fact a bit more. That is, when f is a function defined on a closed interval, and also f is continuous and injective, f inverse is also continuous. In general, if you have f that maps from a compact metric space to some other metric space, and f is continuous and injective, then we can say its inverse is also continuous. Let me know if you wish to see a proof of that fact. But for now, let's focus on the proof for the inverse function theorem in 1D. As promised, the argument that we'll see in this proof is really the same as the proof we did yesterday, that is proving the natural log of y is differentiable and its derivative is 1 over y. So let's first start by picking an arbitrary point y0 in the range of f. We need to show that the limit f inverse prime evaluated at y0, which is the limit of f inverse y minus f inverse y0 divided by y minus y0 as y goes to y0, exists. So we want to show the derivative exists essentially. And next, we're going to introduce the change of variables x equals to f inverse y and x0 equals to f inverse of y0. So the numerator in the limit now becomes x minus x0. Next, we're going to use the inverse substitutions. Since x is f inverse of y and x0 is f inverse of y0, we can write y equals to f of x and y0 equals to f of x0. The denominator of the limit is now changed to f of x minus f of x0. And then we're going to perform an algebraic sleight of hand, that is, to bring the x minus x0 down to the denominator. The desired limit from the beginning is now written as the limit of 1 over f of x minus f of x0 divided by x minus x0 as y goes to y0. So far, we've only used the definition of derivatives, the definition of inverse functions, and an algebraic trick. And next, let's make use of the fact that f is differentiable. Since f is differentiable at x0 in AB, by the definition of derivatives, we have f prime of x0 equals to the limit of f of x minus f of x0 divided by x minus x0 as x goes to x0. What we're going to do next is to change the subscript of the limit sign from x goes to x naught to y goes to y naught. And of course, we'll provide justifications for doing that. We claim that by the fact that the inverse function x equals to f inverse of y is injective and continuous at the point y equals to y naught, we can change the subscript of the limit sign. That is, the limit of f of x minus f of x naught divided by x minus x naught as y goes to y naught is the limit of the same expression as x goes to x naught. Let's see how that's done. We'll use an epsilon delta argument. So first, let epsilon greater than 0. And by the way, just a quick reminder, when we write let epsilon greater than 0, what we mean is let epsilon be an arbitrary but now fixed positive real number. And for the rest of this argument, we're going to work with that epsilon that is fixed. So with an epsilon in our hand, we can apply the definition of limits. And since f prime of x naught is the limit of f of x minus f of x naught divided by x minus x naught as x goes to x naught, there exists a delta greater than 0 such that if x minus x naught absolute value is greater than 0 and less than delta, we have the difference quotient minus f prime of x naught absolute value less than epsilon. That's the classic epsilon delta definition of limit. Next, we're going to use the fact that the inverse function is continuous. Since the inverse function x equals to f inverse of y is continuous at y equals y naught, there exists yet another positive real number delta prime such that if y minus y naught absolute value is less than delta prime, we have x minus x naught absolute value less than delta. And bear in mind, the delta in this line is the exact same delta as we had in the previous line. So what we're really trying to do is to create a flow of implication, if you wish, so that you can go from y being close to y naught to the difference quotient being close to f prime of x naught. So that's the idea. But there's one small detail to take care of. That is, in the front part of the implication star, we also need x minus x naught absolute value to be greater than 0. And that can be justified by the injectivity of the inverse function. So we write, also, since the inverse function is injective, if y is not equal to y naught, then x is not equal to x naught. So let's combine this with the previous implication. We obtain the statement, if y minus y naught absolute value is greater than 0 and less than delta prime, we have the absolute value of x minus x naught is greater than 0 and less than delta. And let's call this implication double star. So now we can see the front part of the implication star is the same as the back part of the implication double star. So now star and double star can be connected if you wish. Now let's wrap this up. Let's suppose the front part of the implication 2, that is, suppose that y minus y naught absolute value is greater than 0 and less than delta prime. By double star, we have x minus x naught absolute value greater than 0 and less than delta. But then by star, we have the difference quotient minus f prime of x naught absolute value is less than epsilon. So we write, suppose y minus y naught absolute value greater than 0, less than delta prime. By star and double star, the difference quotient minus f prime of x naught absolute value is less than epsilon. And because this epsilon is arbitrary in the beginning, we have shown that for every epsilon greater than 0, there exists such a delta prime greater than 0, such that if y minus y naught absolute value is greater than 0, less than delta prime, we have the difference quotient minus f prime of x naught absolute value is less than epsilon. Okay, I know this is a really long sentence, but there's no other way to it because that's literally the definition of limit. To summarize, what we managed to show is, since epsilon is arbitrary, this proves that the limit of the difference quotient as y goes to y naught is f prime of x naught, which is exactly the same as the limit of the difference quotient at x goes to x naught. So this justifies the swapping of the limit subscript as claimed. So at this point, the proof is essentially finished. Let's just write a few concluding sentences to wrap this up. So therefore, f inverse prime at y naught is equal to the limit of 1 over f of x minus f of x naught divided by x minus x naught as y goes to y naught. You recall, this is the algebraic manipulation we did from the beginning. And next, we can use the quotient law of limit. That is, we can bring down the limit sign to the denominator because the limit on the denominator exists is equal to f prime of x naught. We spent most of the proof arguing exactly that. So now we have 1 over f prime of x naught. And since x naught is f inverse of y naught, we have 1 over f prime evaluated f inverse y naught. And since y naught is arbitrary, we have proved that f inverse is indeed differentiable with f inverse of y equal to 1 over f prime evaluated at f inverse of y for every y in the range of the function f. That is the set f of AB. So that's it for today's video. I strongly recommend watch this video in parallel with yesterday's video to see how this proof is motivated. So yesterday's video is essentially a motivation for the proof of the inverse function theorem. That's it for today. Thank you very much for watching, and I'll see you next time. Bye.